Greetings of the day, dear students. In this video, we will discuss about the characteristics of a JFET, that is the junction field effect transistor. We will discuss its characteristics, namely the drain characteristics and transfer characteristics, its a circuit diagram, and also what do you mean by ohmic region. And in this entire graph, how do you understand the ohmic region? What do we mean by saturation region, breakdown region, and what could be the x-axis variable and y-axis variable, right? While plotting the characteristics, what are the different regions we are having? And also we will discuss the JFET characteristics when an external bias is applied. When an external bias is applied, at that time what could be the characteristics, right? And also we will discuss about the transfer characteristics between which two parameters the transfer characteristics of a JFET are to be plotted, in the sense what could be the x-axis variable and what could be the y-axis variable. All those things we are going to discuss in this video, right? Dear students, with respect to any characteristics, whether it is a diode or transistor or some JFET, or with respect to the motors or generators, the very important point is for which parameters the graphs are to be plotted. Very important. What could be the x-axis variable and what could be the y-axis variable? If it is diode VA characteristics, if you remember, we have plotted the graph between the voltage and current, right? Similarly, here also with respect to the JFET, what are the different variables we are having? This is the symbol for JFET, right? And this is the source, drain, D for drain, S for source, and G for gate, right? And now it is a PNP transistor, PNP JFET, or is a N channel. It's not PNP, NPN. Yeah, NPN JFET if you are considered, then obviously this source will be N and this gate will be P positive and the drain also will be negative. This is a N channel JFET. N channel JFET. If you recollect our previous basics, in N channel JFET, source will be N type, drain also will be N type, and gate will be P type, right? So this is the symbol. Now VGG indicates the gate voltage with respect to the ground, right? And VDS indicates the source drain voltage or drain to source voltage, and RL, the resistor, load resistor, you have connected to the drain terminal, and VGS is the voltage between the gate and source, and VDS, as I have told you already, I have told you VDS. RG, in order to make the ground, the gate terminal not floating in air, and a resistor RG is connected in series to the gate terminal. Now with respect to the drain characteristics, if you plot the graph between the ID, the drain current, versus VDS, very important, ID and VDS for different values of VGS, for different values of VGS, how will be the graph of drain current versus VDS? These two parameters are important. VDS versus ID graph is to be plotted for different values of VGS. Then it will come under drain characteristics. Similarly, the transfer characteristics, we will plot the graph for ID, drain current versus VGS, for different values of VDS. This is very important. Throughout the discussion, dear students. It is very important to remember the variable names between which two parameters the graphs are to be plotted. Right now, let me discuss about J-effect drain characteristics when the VGS value is made 0. VGS value is made 0. Gate source voltage is equals to the 0 volt. Then at that time we can observe 4 different regions of operation. One is the ohmic region. In this graph we can observe between 0 to A. In between 0 to A, that region is called ohmic region. If you recollect the Ohm's law, V directly proportional to I, right, and V equal to IR, where the voltage and current varies linearly. For example, here you can observe from 0 to A, almost the relationship between the voltage and current is almost linear, seems to be like a straight line, right, for different values of VDS. Even though you are increasing the value of drain and source voltage, the current ID is also increasing, but this will be not the case throughout the operation. Up to certain extent only it will seems to be linear. After crossing one point, okay, it won't be linear further. Now ohmic region, OA indicates the ohmic region. In this region the J effect almost behaves like a ordinary resistor. Now this point A is called the knee point. This point A is called the knee point, KNEE, knee point, right? Now once it has reached the point A, in the region, the curve AB, in the curve AB region, you can observe it is not that much linear. With the increase in the VDS, right, we will reach a point where slowly, if you are increasing the value of VDS, drain source voltage is getting increased. You will reach a point B called pinch off voltage. You will reach a point B where the current further will not increase. Very important. The current keeps on increasing up to point B, where from there onwards, even though you are increasing the value of voltage, the current almost remains constant. Very important, dear students. The current almost remains constant. Once another interesting feature also you can observe, up to this value of current, drain current remains constant only up to certain point of VDS voltage. Once VDS drain source voltage has crossed a certain point, from there onwards the current will be no more constant. All of a sudden there will be a breakdown. There will be high rise in the current. There will be high rise in the drain current. Very interesting features we can observe in these characteristics. To some extent it behaved like a linear resistor. After that point it is not linear. After the point B, pinch off region, in the pinch off region the current is behaving like a constant current source. Once it has crossed the breakdown region, from here onwards it is behaving like a constant voltage mode, constant voltage behavior it is expressing. So 4 different shades it has shown us, we can observe, right? Yeah. Now point B, in the area from B to C is to be called as saturation region. The area B to C is to be called as saturation region, right? Now here the BC is called the pinch off region. The BC is to be called as pinch off region, and also this is also known as saturation region or amplifier region. 3 different terminologies we have come across. One is the pinch off region, another one is the saturation region, and another one is the amplifier region. In this region the J effect is operating as a constant current device. The current is no more getting increased. It is maintaining a constant even though the value of VDS is increased. It is not depending on VDS. It is independent of VDS in this particular region. That is very, very important, right? So this is due to the fact that the VDS increases, the channel resistance also increases proportionally. Because of the increase in the channel resistance, what happens? The drain current ID will be practically constant, right? And it reaches a saturation that is to be denoted with the variable IDSS. IDSS, saturated, right? Now this is all happening without any some external bias. VGS equals to 0. So here the drain current is now given by the equation, Shockley's equation. This is called the Shockley's equation. The drain current ID equals to IDSS, saturated current IDSS into 1 minus VGS. Of course, derivation not required for you now, right? So VGS divided by VP naught, pinch off voltage. VP naught indicates the pinch off voltage. VGS is the gate source voltage. VGS divided by VP naught whole square. And this also can be written as IDSS into 1 minus VGS by VGS of pinch off voltage square. So now it is the normal operating region of the JFET, right, which when it is used as an amplifier. Now the breakdown region, already I have explained you. In the breakdown region, after once VDS has crossed a particular voltage, once it has crossed this value, all of a sudden there is a breakdown. From here onwards there is a sudden rise in the current. That is a breakdown region, right? Now this is the PN junction undergoes, because the channel has undergone the avalanche breakdown, because the gate channel is already reverse biased. With more and more increase in the VDS value, there leads to a avalanche breakdown at the gate junction. At the gate channel PN junction, it will undergo avalanche breakdown. Just we have discussed with respect to the diode basics, right? It leads to an avalanche breakdown, right? Yeah. Now these are the 4 different modes of operation. Dear students, I repeat again. One is the ohmic region. O to A is called ohmic region. In A to B, it is not linear, right? It is inverse square law rate up to the point B. It is increasing in the form of inverse square law rate, right, up to the point B. Now B to C is called the pinch off region, where the current will be constant. Even though you are increasing the voltage, the drain current will be constant. Now in the breakdown region, even though once you have crossed some breakdown voltage VDS, right, due to the breakdown at the gate junction, which is already reverse bias, it leads to the high rise in the drain current, right? Yeah. Dear students, please remember, y-axis is drain current and x-axis is VDS. Very, very important. X-axis is VDS. Now JFET characteristics when an external bias is applied. In the previous videos, or if you have not yet watched the biasing of a JFET, you please watch what are the different biasing techniques we are having. One is the self bias, source bias, or with some potential divider circuit, or some self bias, source bias, like the different biasing we are having. Nothing but the application of some DC voltage in order to maintain the voltage and current across the device. That is the bias. Now in this figure, dear students, if you observe, the graph is now plotted for different values of VGS. If you observe, the cutoff region, the pinch off voltages are changing. At this point here it is the voltage. Here for other values of VGS, for different values of VGS, you can observe the pinch off voltage has changed. It is increasing, right? If VGS gate and source, if it is made more and more negative, if it is made more and more negative, at one point the drain current won't flow. The drain current ID, the drain current won't flow. If you have made the gate source voltage, it is coming down, observe. If it is 0, okay. This is the IDSS, saturated current of the drain. Now VGS has been little bit reduced. The gate source voltage is reduced, made less than 0. Like this you are making it more and more negative. With the help of more and more negative, you can observe this point is coming down. The pinch off voltage is coming down. Right? Yeah. And also the drain current magnitude is also coming down. At some particular value of VGS, you can observe the drain current is almost 0. But after crossing some VDS, it leads to a sudden breakdown. Because of this breakdown, here we got a rise in the current. This rise in current is due to the breakdown of the gate. This rise in current is due to the breakdown. Up to here the drain current is 0, right? So these are the characteristics you can observe in this discussion. The entire key point is, if VGS, the gate source voltage, is made more and more negative, the drain current will come down. The drain current will come down, right? And this sudden rise in drain current is due to the breakdown of the gate, because it's reverse biased condition, right? Now this DS, the relationship between the drain source voltage, this equation we can understand. The drain source voltage, this voltage in this diagram, the drain source voltage VDS is given by VDS equal to, dear students, please observe, pinch off voltage VP naught plus VGS, gate source voltage, very important. VDS is given by gate source voltage plus VP naught. VP naught indicates what? From our previous discussion, pinch off voltage. From our previous discussion again, how do you understand that pinch off voltage? This corresponding point B, VP naught. This is the from that point onwards, the drain current will be constant. From the point of voltage from where the drain current is maintained constant, that voltage is the pinch off voltage. Very important. Pinch off voltage VP naught, right? But this is not the cutoff voltage. That point please remember. This is the pinch off voltage, not the cutoff voltage. So dear students, this equation is very important. The drain source voltage is equals to pinch off voltage plus gate source voltage. Now since the VP naught, the pinch off voltage will be constant for a given FET, for a given junction field effect transistor, its pinch off voltage will be constant. So the value of this VDS decreases as VGS becomes progressively more negative. The gate source will be always reverse biased. Dear students, please remember, gate source will be always reverse biased. If it is ideal or perfect, the gate current must be or approximately almost equal, should be equals to the 0 amps. I hope you recollect this basic. In the previous videos we have discussed this basic. right? Yeah. Now what could be the breakdown voltage for any given gate source voltage? What could be the breakdown voltage? The breakdown voltage is given by VDS naught plus VGS, VDS naught plus VGS. Now as and when VGS, gate source voltage, source, drain, gate. So here VDS plus VGS. Now VGS becomes more and more negative. VGS is becoming more and more negative, keeps negative. VB also keeps decreasing. VB value also will become decreasing. VB means nothing but VB equals to breakdown voltage. VB also will become decreasing. That means for very small amount of voltage, there it leads to the breakdown. Dear students, you can observe here very clear. This is the breakdown voltage. In this case, this is the breakdown voltage. Here, this is the breakdown voltage, like this. So the breakdown voltage is getting decreased when the breakdown, if you are making VGS more and more negative. If you are making VGS more and more negative, the breakdown voltage is also coming down. That means for very quickly it leads to the breakdown. Simply to say, if the gate source voltage is more and more negative, quickly it leads to the breakdown. Very simple. For example, this point, A point comes first or some D point occurs first. A point only will occur first. For A point, for this graph, the gate source voltage VGS is minus 4 volts. But whereas for this graph, the gate source voltage is 0. The VGS is 0 volts. Right? Very, very important. Yeah. So here this is the now the last characteristics, dear students, is the transfer characteristics, as we have discussed earlier. Again, I repeat again, dear students, it's very important to remember what is the x-axis variable and what is the y-axis variable. What is the x-axis variable and what is the y-axis variable. While plotting the transfer characteristics, it is to be plotted between the drain current. Here also drain current only, but now the x-axis is gate source voltage. At that time, drain source is to be kept constant. Now you are not changing the drain source voltage, but in our previous discussions up to now, we have kept on changing the value of VDS. This is the value of VDS. We have kept changing the value for different values of VDS. We have observed the graph of ID versus VDS. But in transfer characteristics, dear students, VDS is constant. Now how the value of drain current changes with respect to the VGS? We have plotted this graph in the negative second quadrant. Have you observed? Why? Because the VGS value will be made more and more negative. So already this is origin. We will move towards the negative. At one time minus 2 volts, minus 3, minus 4, like this we will check. If the gate source voltage is made more and more negative, you can observe the current at this point, the drain current is IDSS is 0. IDSS is 0. right? So with the increase in the more and more negative voltage across gate and source, the drain current will become 0. At initial stage, the VGS is 0, but the current is high. Maximum, right? So in the form of equations, it can be given as ID equals to IDSS into 1 minus VGS by VP naught. This can also be written as IDSS saturated current, drain saturated current, IDSS bracket of 1 minus VGS divided by VGS of whole square. So this is the final equation, right? Now these transfer characteristics are plotted between the ID versus VGS, right? These are the things to be remembered. So this is all about the characteristics of JFET, characteristics of junction field effect transistor. Dear students, I repeat again, in this entire graph, up to certain region, the relationship between voltage and current is linear. After crossing certain point from A to B, it is not having a linear relation. After crossing the B point, in the pinch off region, the current is kept maintaining constant. Even though you are increasing VDS is also increasing, but the current is maintained constant. It is behaving like a constant current source. Once you have crossed a certain point of VDS voltage, all of a sudden it leads to a breakdown. There is a sudden rise in the drain current. 4 different modes of operation we can observe, right? These are to be highlighted. I repeat again, dear students, please remember what is the x-axis variable, what is the y-axis variable for any characteristics, and highlight these figures, indicate the names of the variables, draw the current directions, voltage polarities, and specify neatly the variable names, right? Easily you can get the good marks, right? Thank you.